Oh, welcome back, everybody. So I just wanted to sneak in a small lecture session before we actually move on to solving what we did on Wednesday. And this is about the derivation of elliptical orbits. And just to show and convince you that we actually get elliptical orbits, which is a part of Kepler's laws, from the solution of a differential equation. And then I just want to give you some small hints about exercise or assignment 8. And then we just keep on going. And George is going to be with you guys online, whereas Julie and I, we will just walk around here. And always, never hesitate to ask questions, please. We don't bite, not yet. Okay. Let's just go back a little bit to the things which we did on Wednesday, and I'm going to bring up the whiteboard and just continue that discussion for something like 10 minutes, and then I just wanted to switch back to the programs and which are relevant for solving this specific assignment, in particular exercises 2 and 3. Okay, so the thing which we did on Wednesday was actually to solve a differential equation, so which started like this. So we had the second derivative with respect to time, and then we had a force, the radial force, so this is a radial velocity, and then we had this angular momentum part, so we have assumed that angular momentum is conserved. And then we had an additional differential equation for the angular velocity, which is now simply given by the angular momentum, not squared, but just L. And this is divided by mu times r cubed. And then the thing which we have in the homework now, homework 8 and exercises 2 and 3, is a force R, which goes like minus K times R. But what we did in the exercise or not on the exercise, but actually during the lecture on Wednesday, so this was on March the 31st, or the 30th actually, then we had the gravitational force. And in that case, when we just looked at the radial component, we have something which goes like a minus alpha divided by r cubed. So when we solve the differential equation as a function of the angle for this specific force, what we found then was a very neat and simple relation, which gives the radius as a function of the angle in the polar coordinates. So we're just looking at motion in a plane. Yeah, go ahead. Say it again.
Should these be r cubed or r squared?
So this is an r squared.
Okay.
Because remember now that this is just a radial component. So what we typically did, in order to get the vector, we multiply that with a unit vector. And when you have the unit vector, you have vector r divided by the magnitude. And then we got the vector r divided by r cubed. So this is just us specializing to polar coordinates. And when we specialize the polar coordinates, we are just looking at the differential equation in terms of the radial degrees of freedom, which is the equation for the radial acceleration. And then we have an equation for the angular velocity, which is d phi dt. So instead of x and y, we are now solving things in terms of r and phi. So that's just the change which we made of variables. And the thing which is neat with this change, which we could do, because we went to the center of mass frame, then we found that since we only had internal forces, and a force which depends on the relative distance, is that angular momentum is conserved. When angular momentum is conserved, it means that we could just look at motion in a plane. And motion in a plane means that we can then just look at x and y, or we can look at just r and phi. as degrees of freedom. Now, for the harmonic oscillator, to go to R and phi is actually something which complicates life. But if you have a force like the gravitational force, or if you're looking at electrostatic interactions with a Coulomb force, then going to spherical coordinates or polar coordinates allows you to find an analytical solution. So you will encounter many of these kind of tricks in physics. So sometimes if you, like when you're taking a course in electromagnetism, one of the cases you're looking at is an electromagnetic field in a sphere or a cavity. In that situation, you would typically transform everything to spherical coordinates, and sometimes you can find analytical solutions. So this kind of bag of tricks is something you will see again and again in physics cases. When we do it numerically, however, we can solve things in Cartesian coordinates, or sometimes it actually simplifies even the numerical calculations if we switch to polar coordinates. And this is what you're seeing in exercise 3 in homework number 8. Because there, when we deal with the Cartesian coordinates, we need to deal with X and Y. Whereas when we go to polar coordinates, we just need to deal with R. So that's things which are useful tricks and tools when you're analyzing a physics problem. You're going to see these things again and again, actually. So let's take a look at the differential equation which we got then. And the solution we got for this specific case. So we had 1 plus this epsilon times a cosine phi. And if we put epsilon equal to 0, then we have simply a circular orbit. Now, these constants, this epsilon, was then given by a constant in front of the different, this A is just a constant in front of the cosine solution. And then we had alpha divided by mu. And this variable C is something which we simply labeled as a new variable, which now depends. So the C is given by L squared. These are the physical parameters of the system you're looking at. And alpha, in our case, if we look at the gravitational force, that contains the gravitational constant and the masses of the two objects which are interacting. So this is, a C is something which contains the physical parameters of the system you're looking at. Now, if we put epsilon, this epsilon is actually called the eccentricity. And if we put epsilon equal to 0, then we have that the radius is just a constant. And that means that we just got circular motion. If we put this epsilon between 0 and less than 1, what we are going to see now is that this actually gives us an elliptical motion. And this is what I wanted to show you today. Then if we put epsilon equal to 1, we are going to get a parabola. If we put epsilon larger than 1, we are going to get a hyperbolic motion. Now, on Monday, when we are going to wrap up things, we are going to show how this relates to the energy of the system. And then we are going back to the figure of the potential energy. And we're going to look at where on the potential energy you are and how that leads to a specific value of this eccentricity epsilon. So there is when we wrap up things on Monday, you're going to see an explicit link between the energy of the system and the type of motion you're going to have. And this is something you can actually extract from this simple solution R of phi. And that's pretty neat, because that gives us a deeper insight about the kind of motion we get under these specific forces. And these are actually realistic forces which we encounter in our daily life. One of the reasons we walk on Earth simply due to the gravitational force. Right? Just to put it in a more practical terms. Okay, so let's now see that we can get this type of motion. And the thing we're going to look at, just to remind you also quickly of what we did on Monday, is that we found an R min which was given by, this is the minimum radius, which is 1 plus this epsilon. And then we had an R max. So this is just a reminder of what we saw on Wednesday. Now, if we now go to the, back to the link with the Cartesian coordinates, we know that R is cosine phi. So we can actually, with this solution, we can translate everything back to Cartesian coordinates if we want to. Now, if I take the equation which we have here, so what we found is that R of phi, and I'm just going to write this as R here, is given by the C of 1 plus epsilon times cosine phi. And then we are simply now going to multiply on both sides. So I multiply away the denominator. So I have R of 1 plus epsilon of cosine phi. So what comes now is just a simple manipulation. And then this is C. And then what we know is that R times cosine phi, as we said, is equal to X. So we can rewrite this in the following terms: R plus epsilon times X is equal to C. Or I can rewrite R as C minus epsilon times X. So what is going to come now is just a manipulation of these equations, so that at the end, we can see that this leads to elliptical motion. So that's, so just be patient with me a little bit, just a few lines of algebraic manipulations. And what we have then, if we now square both sides, and you should keep in mind then that R squared is now, since we are using polar coordinates, is X squared plus Y squared. And if we square the other one, what we have is, we have C squared plus epsilon squared times X squared minus 2 times X of epsilons times C. And then we can get rid of some of the terms, we can simplify some of the terms. So I can rewrite this as an X squared of 1 minus this epsilon squared plus 2 times C of epsilon times X plus Y squared is equal to C. The next thing we do now is to divide by 1 minus epsilon squared. And we define a new constant and define. So we're going to play around with different constants here. So C times epsilon of 1 minus epsilon squared. So we're going to meet A's, B's, and C's and D's. And this may sound like me trying to learn the alphabet again, but I'm just picking, these are just constants which we are using to manipulate equations here. So the when we do this, we can then rewrite the equation. When we now do these manipulations, we will get an X squared plus, and now we have the C of epsilon of 1 minus epsilon squared. So we get a 2 times D of X plus of Y squared. And this contains 1 minus epsilon squared. And this is equal to this constant C squared of 1 minus epsilon. So C contains the angular momentum, the mass of the system, and the gravitational constant and other constants which define the system. Now, one of the things you typically do then is that you want to complete the squares. So you add on both sides, add D squared to both sides. So this is just to complete the squares. So if we do that, then we can rewrite the left-hand side as X plus D squared plus a Y squared of 1 minus epsilon squared. And this is equal to C squared of 1 minus epsilon squared plus D squared. And we can rewrite this in terms of, if we now look at the right-hand side, if I now do the algebra, I bake in this new constant D, which I have here, which is D squared, and I plug that one in. You can then see that the right-hand side can be rewritten as a c squared divided by 1 minus an epsilon squared and epsilon squared. And now we call this a new parameter. So we call this an a squared. I promised you that I'm trying to learn the alphabet again. So I redefine that as a new constant. And then we divide by this parameter, divide by a squared. But then we define also a new parameter. So this never ends, guys, eh? So define b equal to a times 1 minus epsilon squared. And what you will see then is that you can actually define d as a times this original constant c. And then if we do that, then this equation becomes x plus d squared divided by a squared plus y squared divided by b squared, and that's simply equal to 1. And that's something, when we do this manipulation, this is an ellipse. So the thing I just wanted to plot for you now, just to, when we now look at this, so what you're having is actually something which is displaced from the origin along one of the axes by x plus d. And then you have your y. So if d is equal to 0, this becomes just a circle, right? Because if d is equal to 0, then what we have then is simply just the equation for a circle. Now, so let's just make a small graph and convince ourselves about what this looks like. So if you think now of a simple plot of this. So if you look at this x plus d, this simply reflects the fact, if we think of the sun, if we think of the sun as the origin, that our origin, that it should actually be that here, our origin, which is the sun, in our case, we keep the sun at rest, is not at the center of the ellipse. So let's try to make a drawing here. So if you now think of this as the center of the ellipse, then it has a height here, which is called b. Then, if you now think of the sun here, which is our origin, so you could think of the sun or just another kind of mass center, then this goes out here, and this corresponds to this r min. Then we have a distance here, over here, which now contains a from this point to here. And then we have a new distance here, which is d. Now, this whole distance is what we called r max on Wednesday. So what we get then when we make a plot here of the full thing, so we would have something which goes like that. So the height of the ellipse would be 2 times b. And this is the best way I can draw an ellipse here. And we would have this point here, which is our c. And then we have the angle phi, which is this one. So phi is an angle which goes from 0 to 2 pi. So if d is equal to 0, this just becomes a plain circle. And the thing which we are going to discuss in more detail on Monday is how we relate these two energies of the particles, or these objects which we have. So in astronomy, this R max and R min have a specific name. Do you remember what these names are called? So these would be the distances from the sun. Yeah, exactly. So it's perihelion and aphelion. So for the Earth, do you remember roughly what's the relation between what's the aphelion and perihelion like? Are they equal to each other, or they differ a lot? They're only a little bit different. They're almost the same. So for the Earth, if we think of the Earth has almost a circular motion around the sun. If you look at other planets, like Mercury or Jupiter or many of the other ones, they actually have a larger difference. So they have a much more elliptical type of motion. But the Earth happens to have a perihelion and an aphelion, which are almost the same. They're pretty close. So you see now from this kind of very simple differential equation, which we manipulated on Wednesday, we can actually extract a lot of physics information here. Now, the thing we are going to do on Monday, so I'm just anticipating what we're going to do on Monday, because then we are going to link this with the energy which the objects have, and then the type of orbit you can expect. So I haven't showed you this. So let me just bring this up so we have a kind of motivation for Monday. So on Monday in this coming week, what we are going to do then, on Monday, we're going to wrap up this discussion, and then we are going to link this type of motion, which we see, with the potential energy. So we have R of phi, which we have found. This is R. And then we have the potential energy here, V of R. And then we are going to see now these different cases where we have epsilon equal to 0, which is a circle. The energy is going to be less than 0, and we are going to be here. This is at our minimum value, and this has an acceleration which is equal to 0. Then the next thing which we are going to see then is if we place ourselves here, this was the R min which we found, R min. And then we have the R max here. So this is going to correspond to 0 less than epsilon less than 1. And this is going to be an ellipse. The energy is still going to be less than 0. So we call this bound motion. So you're bound to move around some origin, and you don't escape that type of motion. So luckily for us, I mean, the Earth is not escaping its orbit. Hopefully that stays like that for some time. Then we have the next situation. Suppose now we are here in this place. That's going to correspond to epsilon equal to 1. This means that we have an ellipse with an infinite elongation, actually. This is going to correspond to a parabola. And E is going to be equal to 0. So that means that potential energy and kinetic energy, they cancel. And then when we look at epsilon larger than 1, that could be a situation where we are here, for instance. That's going to be a hyperbola. And the energy is going to be larger than 0. So on Monday, we are going to link the energy graph, or the potential energy graph, with the calculation of the energy, and we are going to link it with the values of this eccentricity epsilon. So that gives us a very powerful tool to analyze a physics problem. By simply just looking at this graph, we have the analytical solution, and then we can just look at what does that mean for the energies, and what kind of physics can we extract from this. So what you could say with a hyperbola, you could have a comet coming in towards the Earth, and then it gets deflected, and then it disappears. So that would be a hyperbola. So if you have an ellipse or circle, you're bound to move around a given origin, which in our case is defined as the sun. Any questions so far? I think this is actually one of the more fun parts of this course, actually. So when we started with those falling objects, I guess many of you were not too excited. So hopefully you think this is a little bit more exciting, yeah?
In sci-fi movies.
Gravity system, would that be a epsilon greater than 1 situation?
Any more questions or observations, comments? So I wanted just to give you a little bit a small hint from the homework now, in particular the numerical part. So basically you have, again, almost a solution of the numerical part in the slides. I hope you don't get offended by that. So let me just quickly go back to that, and then I'm going to stop. I actually said I was going to talk for 15 minutes, but I've been talking too much. So let me just quickly do that and just go to the Jupyter notebook. Now, in the Jupyter notebook or in the lecture slides, what you find first is a plot of the harmonic oscillator potential. And we are going to place ourselves at the minimum. And that allows you to find the minimum radius. When you write the code here, there is first a code which runs everything in Cartesian coordinates. And this is a standard harmonic oscillator equations. And you will see now that all arrays are defined as arrays which depend on the number of time steps and the dimensions of the problem. So this is actually a matrix. And the only thing we do now is to define the acceleration to be given by the radius as a function of time here times omega squared, as you've seen before. And this is solving the same problem in Cartesian coordinates. The harmonic oscillator is a special case because in Cartesian coordinates, you have an analytical solution. So if you had time to watch the videos which we put on during the weekend, actually that goes through a lot of the discussions around the exercise here. And if you plot it, you get what you will expect. The only thing is that now you're solving the problem in 2 dimensions. And when you solve things in 2 dimensions, you can actually get solutions which will fluctuate a little bit more. But you see typically because you have more dimensions to deal with. And you will typically see that the radius squared is something like it is 1 plus some error, which is 10 to the minus 7. And this depends on your time step size. Now, when you then shift to polar coordinates, then you just need to look at the radial dependence. And what I've done here is now to define a constant which you need in the calculation, which is the angular momentum squared divided by the mass squared, which then is going to be part of your acceleration, because your acceleration is going to be given by this constant divided by r cubed. And then you have r times omega squared. So this term which you see in here for the acceleration is now you bringing in a term from the kinetic energy, which goes C1, which goes like angular momentum squared divided by mass squared. And then you have the standard harmonic oscillator piece, which is R times K with a minus sign. And then when you solve the equations, you at the minimum, you have to put in the right initial conditions, which are given by this R min, which are then the initial conditions for a circular motion. So you place yourself here. And I've chosen the parameter, so this R min is equal to 1. You can always choose the parameters you want. And when you run it then, you see that your radius stays constant, which is a clear sign that you're dealing with a circular motion. This is the radius as a function of time. And you see also that the energy is conserved. So these are the kind of observations you will see when you're solving this problem here. So going to spherical coordinates or polar coordinates with the harmonic oscillator is not a benefit. It's actually a complication because you don't get an analytical solution. But for the solar system, which we're going to look at, or the Earth-Sun case, this gives us analytical solutions for the 2-body problem. Okay, I'm going to stop here. I'm sorry, I was thinking of ranting for 15 minutes. I went way beyond, but I hope you can forgive me for that. And now we just spend the rest of the time on solving the exercises. I'm going to take off the recording. And you guys just raise your hand and we just keep discussing, right? Let's just bring this one down.